I want to show you something that I built in response to a real conversation. A few weeks ago, I was at a career fair. I spoke with the process engineering team at AMKOR Technology, one of the largest semiconductor packaging manufacturers in the world. They have factories in South Korea, Japan, China, Vietnam, Taiwan, the Philippines, Portugal, and the United States. I asked them what their biggest operational pain point was. The answer was straightforward. When equipment goes down at any of their global facilities, the path from detection to resolution runs through emails and phone calls. Engineers manually pull data from multiple systems. The diagnosis gets delayed across time zones. On average, resolution takes up to 12 hours. 12 hours. On a tool line running advanced flip chip packaging or 2.5D integration, that is not just lost time. At standard throughput rates, that is quantifiable revenue loss, a customer delivery risk, and a yield recovery cost that compounds across every lot that was running when the fault hit. The data to diagnose the problem already existed. What didn't exist was a system that organized it at the speed the problem required it. This is Apex, Automated Plant Executive Intelligence. Let me show you exactly what it does. Before I touch anything, I want to orient you to what you're looking at. 5 steps, 1 pipeline. Step 1, ingest your data. Step 2, select an incident to analyze. Step 3, review computed KPIs and anomalies. Step 4, read the AI-generated SITREP, the situation report. And Step 5, review recommended actions and copy pre-written executive directives. Raw factory data goes in on one end, a boardroom-ready brief comes out the other. Every step is automated, so no spreadsheet assembly, no manual slide building, no analyst in the middle translating data into language. Let's run it. So, step 1 is ingestion. Apex accepts CSV, JSON, or plain text exports from any manufacturing execution system. It does not require a specific format or template. The schema mapping is automatic. What this means practically is that if your factory in Korea exports downtime logs with a column called tool ID, and your factory in Vietnam exports the same data with a column called equipment numbers, Apex recognizes both of these as the same field. It resolves aliases, maps them to a canonical internal schema, and flags any fields that could not confidently map as data quality issues for human review. I'm going to load the data sets I built for this demo, 53 incidents modeled on real AMKOR operational scenarios. Just going to go ahead here. Upload the Apex data, not my English homework. All right, and let's start ingesting it. 53 incidents ingested. The incident list on the left populated almost instantly. So each row is a normalized incident. Just going to zoom in over here. Line identifier, product identifier, timestamps. These IDs looked hash, and that is entirely intentional. Apex automatically masks tool IDs, product IDs, and line IDs during normalization. The analysis runs on anonymized identifiers. The raw proprietary data never needs to leave the facility network in an identifiable form. Privacy first is not a setting. It is default behavior. 53 incidents, multiple lines, multiple products, spanning a 72-hour operational window. This is realistic data volume for a single factory over 3 days of mixed production. Let me show you what Apex finds in it. Before I select an incident, I want to give you context for what this data set was designed to show. Right now, I'm going to focus in on 3 specific scenarios, where did they go? Which would be incident alpha, beta, and gamma. And then where did alpha go? Oh, here we are. Alpha, beta, and gamma. Alpha is moderate disruption, elevated scrap, some downtime, a calibration event mid-run. The facility is hurting, but still profitable. Margin proxy, positive. Beta is serious degradation. Major downtime spike, yield drop, and the line is still technically above water, but the numbers are deteriorating fast. Gamma is the critical scenario. Yield below 81%, utilization below 77, scrap rate up 257, and a margin proxy that has gone negative. The line is spending more to produce these units than it will recover selling them. I'm going to show you gamma first because it is the most important story this data tells. And then I'll come back to show you how alpha and beta look by comparison because the contrast between the three itself is a feature. This is the KPI strip. 7 metrics computed automatically from the raw incident data. Each one compared against a rolling baseline derived from prior incidents in the same data set. Let me walk through each one. Yield, 80.14%. Baseline, 94.42. That is a 15-point drop. In semiconductor packaging, a yield excursion of this magnitude on a flip chip or advanced packaging line is a significant quality event. Every percentage point of yield loss is units that were built, consumed, material, and machine time that will not ship to customer. Utilization, 76.6. Baseline is 99.11. The line is running at 3/4 capacity. That gap, 22 percentage points of unused plant time, is the machine sitting idle while the problem is being diagnosed. Downtime, 7,234 minutes. That is 120 hours. On a single critical packaging tool line at industry standard throughput loss rate, 120 hours of planned downtime represents roughly $1 million in potential revenue impact. That number is in the SITREP. Apex computes it automatically. Scrap, 0.1184. Baseline is 0.03. That's a 113% increase. More than 1 in 10 units produced during this window was scrapped. Units that cannot be recovered, reworked into conformance, or shipped. Rework, 0.0802, up 98.27% from baseline. The units that did not get scrapped largely went into rework, adding labor costs, cycle time, and further utilization pressure. Going to throughput, 63.67 against a baseline of 65. The line is producing at less than a sixth of the normal output rate. Margin proxy, negative 46,513. Negative. This line is not underperforming. It is actively destroying value. Every unit produced during this incident window costs more to make than it returns. That's the financial reality that email chains and manual spreadsheets were not surfacing fast enough. Below the KPI strip is the anomaly detection layer. Every metric is flagged with a delta, the percentage change from baseline, and a z-score, which measures how statistically unusual the current value is relative to historical variance. Scrap rate, z-score 4.1. Rework rate, z-score 3.92. Downtime, 3.06. A z-score above 3 is statistically extreme. It means this is not noise, not a bad shift, not a seasonal fluctuation. These are process failures. Apex identifies them automatically, ranks them by severity, and carries them forward into the root cause analysis. An engineer reviewing this dashboard does not need to build this table. It has already been built. Step 4, the situation report. This is the core intelligence output of Apex. Everything computed in the KPI layer feeds into a structured prompt that goes to the large language model. The model has been given context about semiconductor packaging operations, AMKOR's global foundry network, and the specific incident data. It returns a structured briefing, not a paragraph of generic text, but a formatted analytical document with distinct sections. High downtime and quality anomalies observed January 20 and 21st across lines with cascading events, starting from sensor faults, leading to quality holds and calibration drift. One outlier downtime event, 820 minutes, among top contributors drive overall downtime to 7,234 minutes. That's the situation in one paragraph. Written in the 30 seconds it took Apex to process the data. The data summary section translates the KPI numbers into plain operational language. What happened, in what sequence, on which tools. Impact section quantifies the financial exposure. 120.57 hours of downtime at 8,500 an hour, approximating in over $1 million in potential loss per affected critical tool line. If multiple lines are involved, which top contributor data suggests, the number scales accordingly. This is the section that I want to spend a moment on. Root cause hypothesis, each one confidence score. 72%. Sensor fault indicating systemic reliability issues in sensors across multiple lines, triggering automated holds and cascading process disturbances. 70%. Upstream process instability led to downstream quality holds and eventual calibration drift, creating a cascading effect of defects and rework. 60%. Maintenance or control system drift on critical tooling contributed to calibration drift and subsequent micro stops, amplifying downtime. 50%. Incoming material or lot quality variability contributed to quality holds and rework, exacerbating yield and scrap increase. These are not guesses. Each hypothesis is derived from event timeline in the data. The sequence of sensor faults, calibration drifts and events, quality holds, and micro stops at Apex extracted from the incident record. This is the starting point for your RCA, not the ending point of a 12-hour investigation. Confidence scores, 71%. Lower than the other incidents in this data set, and I want to be direct about why. The Gamma dataset is missing factory-level site identifiers and fault codes. Apex knows this. It scores its own certainty based on data completeness, and it explicitly lists what is missing. In this case, package type specific failure patterns and the exact count of critical tool lines affected by the downtime and the distribution across factories being unquantifiable. This is not a weakness. This is auditability. The system tells you exactly what it would need to be more confident. You can act on a 60% confidence sit rep while you go gather the missing data to push it to 85%. A system that pretends to be certain when it is dangerous when it isn't is dangerous in a manufacturing environment. Apex shows its work. Step 5, actions. Apologies, getting late. There are 5 recommended actions, each one tied back to the specific KPI metric it is designed to move. Watch the tags beneath each action. In this case, it recommends initiating cross-line sensor integrity audit and sensor reseating and replacement where needed to correlate sensor fault events across lines to identify systemic sensor reliability issues. This is based on its downtime in minutes, the utilization, yield percentage, and scrap rate. This action is not generic advice. It is traceable. The system knows which metrics drove this recommendation and which metrics would improve when it is executed. This traceability is what makes the output auditable. You can defend every action in this list by pointing back to the data that generated it. Conduct cascade path analysis based on downtime, rework rate, scrap rate, yield percentage. Prioritize maintenance engineering for a specific tool and associate the line with the longest downtime based on the downtime, utilization, and margin. Review the incoming material based on the scrap rate, rework, yield percentage, Execute a geographic drift analysis for the next 72 hours to detect potential cross-factory process drift and escalate if 3 or more events occur in any factory based on the utilization, margin, and throughput proxy. And then this, the directives. Two pre-written executive communications. One for containment and rapid diagnostic actions on the affected line, and another one to stabilize production with data-driven RCA ownership and KPI rebounds. These are not templates. They are specific to this incident. They name the tools, they cite the timestamps, they specify the actions and sequences. One click, that message is now on your clipboard, ready to paste into any email. Just like that. A Slack message, a Teams channel, a ticket, ready to go wherever you can paste the text. The communication that would normally take an analyst 45 minutes to draft after a manual review meeting is now generated in the same pipeline at the same time as the analysis. This is what the team at AMKOR described when they said they needed something that explains what changed and what to do about it. Not a dashboard, a decision pipeline. I want to quickly show you alpha and beta so you can see how the same pipeline reads different security levels. So let's go over to incident alpha. Much better numbers in this one. Margin proxy positive, $90,000. Yield at 93%. Downtime of 1,879 minutes, elevated but recoverable. The sitrep identifies calibration drift. The sitrep is going to start identifying the issues, which in this case, I believe should be calibration drift. Prolonged downtime causing microstops. There we go. Calibration drift event with sensors reading drifting outside control limits during mid-run and concurrent quality issues. And then if it loads, it will start to identify when what percentage the calibration drift, its confidence rating that the calibration drift is causing issues. So in this case, it's stated that it's the cascade effect from the microstops are causing the biggest issue. Conveyor jams are another potential issue, and calibration drift is, it's 62% confident that a calibration drift is one of the main issues in this. Notice, same pipeline, same 5 steps, different severity story. Let's go over to line beta and have a look at it. Margins, $20,000, still positive, but declining against the baseline. Downtime, 4,519 minutes. That's 75 hours. Yield at 87.86%. The system is degrading. Sitrep is still generating, so let's give that a second. There we go. In the time it's taken me to read that out, it's already finished the sitrep. It's linked it to extended, is driven by, it's cited in the main prompts are extended downtime, elevated scrap and rework, and reduced utilization linked to multiple overlapping issues on the same line, stating the big issue is a calibration drift and changeover delay tied to a recipe load delay, several microstops. The top contributing tools accounting for the majority of the scrap, rework, and downtime, indicating a systemic instability rather than a single point failure. Yield dropped 5.49%. Let's go down and have a look at the sitrep confidence. 67%. Higher, I believe this was higher than gamma, which sat at, I believe, 62%, because this data set has slightly more complete event data. Alpha to beta to gamma is not 3 separate incidents. It is one story, the trajectory of an unresolved process failure over time, and apex reach each chapter differently. What you just watched took about 12 minutes to walk through. The actual pipeline from the moment you upload the data to the moment you copy that executive directive takes under 2 minutes. The 12-hour resolution cycle that Drake Miller's team described is not primarily a technical problem. It is an information routing problem. The data exists. The engineers exist. What is missing is the system that connects them fast enough to matter. Apex is a prototype. It runs on synthetic data today. What I would do next with real access to AMKOR's operational data is validate the schema mapping against actual MES exports, calibrate the KPI baselines against the real production history, and build out the cross-factory pattern detection layer, the capability that catches a mold compound issue hitting 5 factories simultaneously before it becomes 5 separate email threads. The foundation is built. The pipeline works. The output is usable. My name is Kieran Fang. I'm applying for the product engineer intern role on the advanced flip chip BGA and Chiplets team. This is the deliverable I bring on day one and the roadmap I'd execute from there. Thank you.